May it please Your Royal Highness. My name is Professor Dr. Supawan Tantayanon, the President of Science Society of Thailand, under the patronage of His Majesty the King. It is indeed a privilege and an honor to extend our deepest appreciation to Your Royal Highness for your generous hospitality extended to the Science Society of Thailand and for graciously presiding over the 46th International Congress on Science, Technology, and Technology-Based Innovation, or STT46 Congress today. The year 2020 marks the 72nd anniversary of the Science Society of Thailand. It is vital to recognize countless success stories and achievements in science under the umbrella of the Science Society of Thailand over the past 7 decades. Regardless of current unusual circumstances due to COVID-19 pandemic globally, the Society has continued with 3 new initiatives this year. First is the transformation of an annual National Congress into an international meeting, the STT46 Congress. It covers several global aspects of science, from the very fundamental to practical applications of the basic principles of sciences. Secondly, the Society believes in attracting and stimulating the passion in young, innovative minds by rewarding undergraduate students early in their academic career. The Young Rising Stars of Science Award program has been initiated to recognize outstanding undergraduate research projects in every scientific disciplines and curriculum of all universities in Thailand. This year, we received the applications of 91 projects. The students will present their work here at the STT46 Congress, where they will get the opportunity to learn from the experts, discover new areas outside of their fields, and contemplate on the direction of their future careers. Thirdly, UNESCO has adopted a resolution to proclaim 2022 as the International Year of Basic Sciences for Sustainable Development, announced in November 2019. The year 2020 will highlight the crucial role of basic sciences on sustainable development toward the United Nations Sustainable Development Goals, SDGs, milestone in 2030. In preparation for this significant event, the Society called for the assembly of all basic sciences department heads in Thailand at this Congress. STT46 Congress will be a stage for the scientific community worldwide to communicate and collaborate in the search for sustainable solutions that will benefit all life on Earth. On behalf of the Science Society of Thailand, I am grateful to the Faculty of Science, Yrามคำแหง University, our terrific co-host of the STT46 Congress. Appreciation is also extended to all the chairs of sessions, symposiums, the plenary, keynote, and invited speakers, and certainly all the participants and the sponsors that have contributed to the success of the STT46 Congress. May it please Your Royal Highness, on behalf of the Science Society of Thailand, may I present 22 awardees, one sponsor, and the co-organizer of the STT46 Congress to receive commemorative plaques for their achievement and contributions to the Congress from Your Royal Highness. The Senior Scientist Award, Associate Professor Dr. Napawan Noparat Narapon. The Outstanding Scientist Award, Professor Dr. Suthichai Atsa Bamrungrat, and Dr. Wannop Viset Sangwan. The Outstanding Technologist Award, Professor Dr. Phiupan Maliwong, and Dr. Apichat Intara Panit. Young Scientist Award, Dr. Thavitam Limpanuphap, and Dr. Pithiya Pathana Sattayawong. Young Technologist Award, Dr. Kathawut Namdi. Outstanding Science Teacher Award for tertiary level awardees, Associate Professor Dr. Suchana Chawanit, and Assistant Professor Dr. Somporn Choi Ari. For vocational level awardee, Ms. Suporn Si Ngen Yuang. For secondary level awardees, Mr. Kietisak Inratsadon and Mr. Suthipong Jai Kaew. For primary level awardee, Ms. Janpen Kong Bamrung. Science Project Award, Vocational Level Awardees, Chaya Industrial and Community Education College from Surat Thani. And Samut Sakhon Fisheries College from Samut Sakhon. For upper secondary level awardees, Bangkok Christian College from Bangkok. Damrong Raj Songkhraw School from Chiang Rai. And Princess Julapon Science School from Phetchaburi. For lower secondary level awardees, Hoi Nam Hom Vityakan School from Nakhon Sawan. Bangkok Christian College from Bangkok. And Princess Julapon Science School from Chonburi. The sponsor, Bangkok Bank Public Company Limited, Mrs. Ratchani Nopmeung. The co-organizer of STT46, Faculty of Science, Yrามคำแหง University, Associate Professor Dr. Wanna Musik. May it please Your Royal Highness.
May it please Your Royal Highness. My name is Professor สมเกียรติงามประเสริฐศิษฐ์ the Chairman of the Organizing Committee of the 46th International Congress on Science, Technology and Technology-Based Innovation, or STT46. The STT46 Congress is hosted by the Science Society of Thailand under the patronage of His Majesty the King and Faculty of Science, Yrามคำแหง University during October 5 to 7, 2020 at Yrámคำแหง University. It is devoted to the theme Power of Science to Achieve SDGs. The discussions we have in the near few days will serve as a contribution to SDGs. The Congress is composed of 5 sessions and 16 symposiums chaired by the eminent scientists. The 5 sessions are Challenge in the Frontier of Physics, MathStatCom in the Digitally Innovative Era, Impact of Biological Science to SDGs, Responsible Chemical Science for Future Sustainability, and Innovations for Sustainable Future. The 16 symposiums are in the interesting current issues such as 360-degree COVID-19, climate change in a changing world, green and sustainable chemistry, etc. The technical program is thus rich and varied with 3 plenary speakers: Professor Dr. John Warner, the 2014 Perkins Medal, which is the highest honor in American industrial chemistry, USA; Professor Sutichai Asa Bamrungrat and Dr. Wanop Viset Sangwan, the 2 outstanding scientists of Thailand, year 2020. For 5 keynote and 50 invited speakers are from various parts of the world as well. The 106 oral presentations are categorized in 5 parallel oral sessions and 187 posters into 2 poster sessions. Besides, there is 1 workshop for the early career students entitled The Future is Now, Science for SDGs. It appears that the Congress is being attended by 1,000 overseas and local participants from 25 countries. Due to the COVID-19 pandemic, we will have a mixed meeting both online and offline. All Thai audiences are here at the Congress, while most overseas participants will have their presentation virtually. May I now have the honor of requesting Your Royal Highness Princess to declare the Congress open.
Science and technology play important roles in the development of world health, agricultural production, economic growth, and social development. Thus, United Nations has declared 2022 as the International Year of Basic Sciences for Sustainable Development, with the aim of achieving Sustainable Development Goal, or SDGs, by the year 2030. Science and technology in Thailand have improved greatly in the last few decades in terms of basic science education, science literacy, as well as advanced research and innovation. Moreover, numerous highly qualified scientists and technologists in Thailand produce research work of international quality. Thus, when the COVID-19 pandemic recently affected the whole world, science and technology plays an important role in mitigating the disease. For Thailand, efficient and successful management helped to contain the spread of disease by bringing together a task force from all fields of science to share knowledge and work together. I am glad to see the development of this year's Congress to international level. This change is most appropriate since international cooperation is essential for the well-being of mankind. The theme and program of this Congress provide a platform for the exchange of knowledge and ideas which will facilitate and achieve the achievement of sustainable development goals. It is my pleasure to declare open this 46th International Congress of Science and Technology-based innovation under the theme Power of Science to Achieve SDGs. I wish the Congress a successful and fruitful outcome.
May it please Your Royal Highness. My name is Associate Professor Dr. Vanna Musik, Dean of Faculty of Science, Yrามคำแหง University. May I have Your Royal Highness permission to introduce three plenary lecturers. First, Professor John Charles Warner will deliver his lecture on all fields of science addressing the United Nations Sustainable Development Goals, online from University of Massachusetts. Second, Professor Dr. สุทธิชัย อัศบำรุงรัตน์ Outstanding Scientist 2020 from Chulalongkorn University, will deliver his lecture on Process Intensification and Multifunctional Reactors for supporting Thailand's transformation to bio-circular green economy. Third, Dr. วรรณพ วิเศษสงวน Outstanding Scientist 2020 from Natural Science and Technology Development Agency will deliver his lecture on From Fundamental Research in Food Chemistry to Innovations and Expand New Horizons for Thailand Food and Feed Industry. May it please Your Royal Highness.
Honored to be invited to speak at the 46th International Congress of Science, Technology, and Technology-based Innovations, the power of science to achieve SDGs. My title of my discussion today is All Fields of Science Addressing the UN Sustainability Development Goals. When we consider the role of science, and particularly chemistry in society, there are many things for us to be very proud of. With chemistry, if we consider the agricultural advances over the years, In 1990 to now, we have seen an increase in 82% global food production. The world's hungry are being fed. And this has been done because of advances in chemistry and agricultural agents such as pesticides, which at the same time, 1990 to now, has seen a 78% increase in use. Hungry people are being fed. But of course, if you open up the newspaper, turn on the radio, look on the internet, we hear about pesticide residues in food, hazards that are happening because of these materials and toxic materials that are impacting. We have the good, but we also have the problems. When it comes to electronics, we see that since 1970, the power of electronic development, the scientists and engineers who have been inventing new technologies for the electronics industry have done amazing things. That the computational power of our cell phone today exceeds the computational power of the space programs that went to the moon in the 1970s. This science and this technology has been amazing. And with that good, there has also been the problems. We hear about electronic waste and the toxicity of these electronic waste and how some elements are becoming endangered. We have the good and we have the problematic. When it comes to energy, alternative energy such as solar energy has advanced since 1975 in an amazing way. One specific type of alternative energy, solar energy, based on solar cell efficiencies, we can see that there has been a linear increase in efficiency of alternative energy such as solar energy. But of course, when we consider the impacts of energy, we also hear about the Intergovernmental Panel on Climate Change, and we hear about the advances of carbon dioxide, and we learn about the loss of ice sheets in Greenland, and we learn about climate change making wildfires, especially here in the United States recently. We have the good and we have the problems. When it comes to pharmaceuticals, the pharmaceutical industry has done amazing things. Since 1975, the chance of surviving cancer has increased profoundly. The 10-year survival rate since 1975 has increased at least 50%. If you look at the 1-year survival rate, it's gone steadily up and up and up. And so there's amazing advances in pharmaceutical sciences. But of course, there's also some problems. We hear about pharmaceuticals in the environment, toxic materials, and problems like that. We have the good and we have the problems. When it comes to materials, also, when we think about it, this is kind of amazing. In 1989, the global production of plastics by volume exceeded the global production of steel. We started making more by volume plastics than steel. And just think of the amazing things that these lightweight and expensive materials have done for housing people from the elements, for clothing people, for keeping their food supplies safe. There's been so many amazing benefits from this. But of course, with the good, there has been problems like plastics in the ocean and toxic materials that are finding their way into the environment. We have the good and we have the problems. When it comes to chemistry and service to society, this is not a surprise. The field of chemistry, the field of physics, the field of biology has always had this duality about it. We've only, even matter, back, a century ago, we started to contemplate the fact that matter can be a wave or can be a particle. So duality is not something new to science. And the fact that we can have technologies that have benefits and can have problems should not come as any surprise. So as we look at the United Nations Sustainability and Development Goals, and we look at all 17 of these, there is a moral and ethical responsibility that as we develop new technologies, we must continue to solve the problems because there continue to be problems for the world in the hungry and the sick and the impoverished. We need to come up with these technologies, but we also must consider how do we do this without causing additional problems? How do we address this duality? If you look on the literature, you find there are so many books, there are so many programs, there are so many ways of looking at this. There's cradle to cradle, there's resilience, there's natural capitalism, there is the circular economy, responsible care, limits to growth, biomimicry, the European Green Deal, Alliance to End Plastic Waste, green chemistry. There are so many different ways that we can approach this. How do we start thinking about this? And I think that the most important thing, in my opinion, is that all of these approaches have merit. Not one of them is better than another. One of these approaches isn't superior to another approach. That different individuals in science and the humanities that are trying to work for a better world, each of these speak to them in different ways. And instead of finding out which one is more important and which one is better, what we need to do is recognize that they all have the ability to contribute to an amazing future. But it requires us to think about things from a different way. It's worthwhile to think about all the materials that we have in our lives, all the things, the things that we eat off, or the things that we drive, the things that we wear. How can we think of these from a bigger picture of the environment? Well, let's think about it this way. I propose this as a suggested way to look. We take natural resources, and we extract them, and we turn them into molecules and ingredients. Then we take these molecules and ingredients, and we synthesize materials and components. These materials and components, then we manufacture into products. And if we do a good job, these products are very strong, very good, very reusable, and so they stay in use as much as possible. We can call this cycle the use and reuse cycle. But of course, sometimes the products can't stay in use and reuse, so then they must go down to the next level, and we have to do what's called mechanical recycling. And so this loop, this cycle here, we can think of as the recycle loop. And things can go from materials and components to products and back and forth between with manufacturing and mechanical recycling. But inevitably, something's going to happen, and we're going to have to go the next rung down, and we have to do what's called molecular reprocessing, so as to do what I call this loop here, materials metabolism, in which we have to learn from nature how to keep things in this level of matter. But after this, the next level down is when we want things to degrade into the environment, into innocuous byproducts, back to natural resources, and this is the regeneration cycle. And then, of course, our ecosystems, we want our ecosystems to essentially stay pristine, to stay stable. And so in a way, we can think of this as what we do on this side, the human-built world, as we use and reuse things. We want them not to have this continuous cycle going around, but actually it is a clockwise, counterclockwise pendulum. And what we want is, as the things that we humans make interact with the natural environment, we want to minimize that as much as possible. So that little over section here, where the use and reuse comes in contact with the stable ecosystem, in my opinion, that is an operational definition of sustainability. That if we can minimize that, if we can make our impacts that are negative on the environment as small as possible, that is how we stay sustainable. But of course, we also need to protect ourselves from the environment too. Our houses protect us from the weather. Our clothing protects us from the climate. So it's a balance. We need to protect ourselves from the ecosystem and the environment, but we need to not damage it. So it's that overlap that we want to mostly focus on and see how can we prevent that interference. It's never going to be zero. Everything we do is always going to have some impact, but we need to find a way to minimize that impact, and tomorrow get better, and next year get better, and in a decade get better, and be on this perpetual journey of minimizing that impact. So let's look at each of these different cycles a little bit different and realize that what we humans do isn't so different than what nature does. If you think about the use and reuse cycle, all right, in nature, a hermit crab will find a shell, and when it gets too big, it leaves that shell and it goes to a bigger shell. That's a very natural thing. It is using and reusing its material. Okay? When we make a car bumper for an automobile, we want that to stay in use as long as possible. If we make a playground, we want that material to stay in use as long as possible. But also, if we make a cup, we want that cup to be reused as much as possible. We drink, we clean, we drink, we clean. And if we can keep things in this use and reuse cycle, sustainability is very good. And what we're doing in this case is we're conserving the chemical composition and we're conserving the form. The shape and the chemistry stay the same. But what happens is this thing called entropy ends up coming to tackle us. And what happens is our beautiful materials, it is inevitable. Something will happen and they will break. And then when that happens, entropy is driving us down the cycle to the next station in the cycle. And in this case, the next station is the recycle station. And this is not unlike nature. In nature, a bird will find different pieces of material on the ground and build a nest. A beaver will chew on a tree and knock down a tree to make a dam. We humans, what do? We take and collect our plastics, we sort them, we shred them, we melt them, we granulate them, and we try to keep recycling the plastics as much as possible. We manufacture and we recycle. We manufacture and we recycle. When we do this, we keep the chemistry the same, but we change the form. It goes from a ball to a shredded little piece to a bar to a shredded little piece. So the shape keeps changing, but the chemistry keeps the same. But again, entropy is going to come in and change this. The more we keep recycling, if these lines here are a bunch of polymers that are the molecules that are these plastics, every time we do recycling, they break down a little bit. And after some point, they break down enough that they no longer work. And so entropy forces us now to go to the next station in our cycle. And the next station is what I call the materials metabolism. And this is the one where I feel there is the most exciting opportunity for us to invent and create and to support our future economy. Because essentially here, what we're doing with metabolism in biology, we take small molecules and we make large molecules. We take large molecules, we make small molecules. When we break down a molecule, we call it catabolism. When we form a big molecule, we call that anabolism. And altogether, that is called metabolism. And what we're going to do is emulate nature and do the same things in a materials metabolism. Here's an older picture of my wife and daughter. My daughter is giving my wife something to eat. Let's think about this for a minute. What happens when we eat food? When we eat food, we break down the carbohydrates to sugars. We break down the proteins to amino acids. We break down the lipids to fatty acids. But if the human body was designed by us humans, we would probably do it very differently. When we break down the carbohydrates to the sugars, we'd probably purify them, put them in little trucks and store them in different parts of our body. We would take the different amino acids, purify them, and put them in warehouses all over our body. But that's not how nature works. That's not how biology works. As the food goes into our intestines and we start to break down the big molecules at exactly the same time, we make new things, right? As we're eating the food, we grow hair, we grow fingernails, we grow blood cells. And so in nature, what happens is the destruction of materials and the construction of materials happen at the same time. But we humans, the way we have constructed industry, this never happens this way. That is an interesting opportunity. But not only that, when nature does it, as we eat our food, we also get energy. So that energy is something, again, that is very unnatural for the way we do manufacturing. If we can learn from nature, if we can figure out how nature does this, we can do some amazing things. The way nature has done it is in this molecule called ATP, in which it constructs this little molecular battery. And what happens is, as we break down food, we charge these little molecular batteries in our cells. When we expend that energy, we discharge these little molecular batteries. So the elegance and beauty of nature that has happened over billions of years has figured out how to do this. We need to learn how, because when we do this, what happens is essentially we're going to have, we want to keep this going until it doesn't work anymore to go to that next station. Now, in this station here, what's really important is we are altering both the composition and the form. That's kind of exciting, because now we have the most degrees of freedom. As we break things and make things, we're changing the chemistry and the form. But of course, eventually entropy will take over and we'll have to go to the next station. And that next station is the regeneration station. This one here, in nature, we have termites that collect things in their mounds. The dung beetle collects things for its community. The bee seeks pollen and moves pollen. Lions will eat their prey. There are abundant examples in nature. And of course, we humans, we're starting to do this. Okay, where we're altering the composition, but we're conserving the form, kind of like we're trying to recycle boxes. In the food system, there's a lot of regeneration of foods where we use the food as fertilizer to grow new food. We have some regenerative textiles, and we're starting to learn to make regenerative cups and things like that. So we're starting to do this, but of course, even this is imperfect. That entropy is going to appear, and we're going to have to go to the final cycle here is the stable ecosystems. And the stable ecosystems are, of course, pictures like this, where we want human activity to have as little or no impact as possible. So the whole picture here, when we look at it, we have all these different levels of organization due to entropy in different scientists and different chemists and physicists and people in the humanities and sales and marketing. Everybody has a role to play in this. But what we're looking at here is that impact between those two cycles. Now, this is an imperfect picture, because not only did this picture describe, if everything happened the way we wanted it to happen, unfortunately, what ends up going on is things don't happen the way we always want them to happen. As we're recycling things, sometimes things fall out and they leak, and sustainability gets a little smaller, because that gap starts to get a little bit broken down. And when we do metabolism, things leak, and sustainability gets a little smaller, and that gap breaks down a little bit more. And then when we regenerate, things leak, and that gap gets a little bit more leaky, and sustainability gets smaller. And so not only is it the things that happen that we want to have happen, but the leakage as well is problematic. But here's the thing. That isn't on one of those cycles. This kind of thing isn't on one of those cycles. This kind of thing is not on one of those cycles. CO2 in the atmosphere isn't on one of those cycles. We've got to acknowledge that there is the planned material, and then there is the unplanned things, the leakage. Now, when we look at this cycle, there are two approaches. There is the behavioral approach, where we can work with marketing and with education and work with people and say, well, hey, let's look at how we can behave better to protect the environment. How can we design products to help people not waste as much, not pollute as much, and do things? There is a lot of work we can do for behavior. And there's also a lot we can do in the chemistry labs, in the biology labs, in the physics labs, in the engineering labs to develop technologies that are compatible with nature. It's not one or the other. They both have to work together so that we can have this future that we're looking for. It's not one person. It's a lot of different people collaborating together to make this happen. And that is the purpose of the field of green chemistry. The field of green chemistry is the design of chemical products and processes that reduce or eliminate the use of of hazardous substances. And as you can see, it's good. There is, what you can tell in the back there, and we'll come back to that book, that's been translated into many different languages, and Thailand is one of the premier countries on the forefront of green chemistry. Green chemistry is a set of 12 principles that say to the inventor, that says to the designer, if we're going to meet the UN sustainability goals, if we're going to protect human health and the environment, here are the things that we need to pay attention to so that we can successfully accomplish our task while minimizing those negative impacts. For a technology to be green chemistry, yes, it has to be more environmentally benign than some alternative technology, but that's not enough. It has to succeed in the marketplace. People must want it. And if we're going to do that, it must perform better than the existing technology, and it has to have the right cost. Only when we have a technology that works better, costs better, and oh, by the way, is better for human health and the environment, then we have green chemistry, then companies can become profitable, sales in stores, the economy can boom, and people can be healthy and happy with a growing economy. We need to have in parallel the invention of next generation technologies to have as little impact on human health and the environment. And so if you accept that who wouldn't want this? Okay, of course, anyone would want something that works better, costs better, and oh, by the way, it's better for human health and the environment. So the only barrier is the invention. And we have to ask ourselves, are we teaching the next generation how to invent technologies that are better for human health and the environment? If we look at it from this perspective, this material cycle that I described, we describe a loop, okay? Natural resources, manufacturing, distribution, use, and collection. And if we do this well, everything stays in a loop. But there's one problem with this picture. A closed loop not only keeps things in, but it also, if we're not careful, keeps things out. If we need inventions to get to a sustainable future, and we have a closed loop, where does invention fit on a closed loop? So I believe that the better analogy is to make a Mobius strip and twist this thing so that it goes around twice, and then it takes two circles. And what we have is first the materials ecology, and then we have superimposed on that what I call the intellectual ecology. That is basic research, applied research, development, scale up, commercialization. And so what we need to do is the education systems must partner with the companies and the industry so that as industry comes up with problems, we can invent the better solutions. And we need to come closer together and understand that a sustainable future will not happen just by hoping for it. It must be invented, and the universities and the industries must work together. And we need a new way of thinking. We need new creativity, new imagination, because Albert Einstein said, no problem can be solved at the same level of awareness that created it. If we keep doing chemistry the way we've always done chemistry, well, we're going to keep making the same chemistry. So we need to rethink how we do this. And a good analogy is, let's say a group of us wanted to build a pond. We would find some space, we would dig a hole, we'd fill it up with water, we'd put in some fish, maybe a frog and some trees. Now, if we spent a great deal of time maintaining it, it would stay beautiful forever. But if we went away for a year and came back, probably everything would not survive because we're not really creative enough. We don't know how to put an ecosystem like this together yet. It's very difficult to understand this. The field of biochemistry figures it out, right? So here is another picture of my wife and daughter. This one here is a pond near our house. This pond survives because over the millions of years, or hundreds of thousands of years at least, everything evolved together. The birds and the bees and the bugs and the beetles, they all co-evolved together to make this stable equilibrium. We humans look at this and we're just now starting to understand. The fields of biology and molecular biology and biochemistry we're studying is just the tip of the iceberg, maybe 5 or 10% of our knowledge that we have now, but we can start understanding these metabolic cycles and how things are put together. And that is where my optimism comes, is that we are just on the first step of the frontier of sustainability. And if we think of it, there's a factory in South America, there's a factory in North America, a factory in Europe, a factory in Southeast Asia. We have the electronics industry, the pharmaceutical industry, the cosmetic industry, the textile industry. Here we are in 2020, trying to find a way to, like that pond, make everything work together, have the molecules and the materials interact with each other, and it's very difficult. And the reason it's difficult is because these things weren't designed to go together. 50, 60 years ago, they all evolved all by themselves. This factory had no awareness of the pharmaceutical industry. The cosmetics industry knew nothing about the factory in Europe. And so things evolved, and now here we're trying to put together things that were not designed to go together. But I am so optimistic. I believe that we can do this if we pull together and we look at it, the tools of chemistry, the tools of biology, and everyone else. If we organize to do this, we can start making better products that make us profitable and also stop this negative impact on human health and the environment. Because the way I look at it, of all the products and processes available to humanity today, maybe 10% help the UN SDGs. 90% of them are just not doing a very good job addressing the UN SDG issues. If we search what has been invented, what's possible, maybe if we do a really good job finding some things that people have done in the past, we might be able to get 25% of those alternatives. But right now, today in 2020, I would argue that over 65% of the technologies have not been invented yet. People aren't choosing not to use these technologies. They don't exist. We need to invent them. And so we need to find a pathway so that we can do this. Because where do products come from? Molecules get turned into materials. We call that basic research. Materials turn into components. We call that applied research. Components get turned into devices. We call that development. And when we do it a lot, we call that manufacturing. This has been going on for a very long time. The only difference is in the last several decades, we've become aware of the environment. We now ask ourselves, where do those molecules come from? At the end of life, where do those products go? When we manufacture, when we sell, when we use these things, who is the only person who can change this equation? The inventor. Because after it's invented, after it's on the market, it's too late. It's already out there. So our opportunity for the future is to change not how we do it after it's invented, but before it's invented. Because there is chemicals policies are there to drive the demand. We need chemicals policies to drive the demand. But we also need the supply, which is the education in green chemistry to teach people. Right now, if every government policy, if every consumer just woke up tomorrow and said, I insist on only having sustainable technologies, they're going to be very sad because we haven't invented them yet. And so we need to invent the technology so that people can use them. Now, of course, we also need the people to want them. So it's a balance between desire and demand. And it's something that I think the next generation and those who care, they're up for the task. I think we can do this. It's not the birth of ethics. It's not like people have never heard of this, didn't care about human health. Of course people did. You know, if you ask people in chemistry, oh, gee, is chemistry dangerous? They'll say, yeah, chemistry has to be dangerous, but it's okay. Because even though chemistry is dangerous, we'll wear gloves to protect our skin. We'll wear masks to protect our lungs. We'll wear goggles to protect our eyes. We'll install filters and smokestacks to protect the air, the land, and the sea. The way we'll protect the environment is to control the exposure. Now, the problem with controlling the exposure is twofold. First, all of this costs money. And so if you're going to protect the environment and it costs money, that's very difficult for business. And the second thing is that they break. every once in a while something goes wrong. So every time we hear about some terrible disaster, like I described at the beginning of this talk, those weren't planned. Those were when these things fail. So the revolution that is green chemistry is looking at us all working together to recognize we have to protect people by mitigating exposure. But over the last 10, 15 years, the fields of toxicology and environmental health sciences have taught us how to address it by hazard itself. And when you can take a molecule that is hazardous or toxic and with the tools of chemistry make it less hazardous or toxic, the money that you spend controlling the exposure goes much down and the risk goes down because it's intrinsically less dangerous. So what are we going to do? If we have all this invention, who is going to invent these technologies? This, I think, is the crisis of innovation, what I call the crisis of innovation, but it's also the opportunity, because the invention of these technologies not only make a better world from a human health and the environment, the moral and ethical components, but it's also more profitable. Faster time to market, more economical. And so we need to look at how people learn green chemistry. Again, here's my daughter reading. Very good choice in books she has there. And of course, as you well know, there is the translation of green chemistry theory and practice in Thailand. Very, very amazed at the work that people are doing in Thailand. The organization Beyond Benign is trying to help with with children learning, just small children learning how to be inspired to try to go into the sciences to invent better technology, but also the universities to be able to teach the future generation how to invent and make better technologies that are consistent with the United Nations Sustainability Development Goals. And so there are about 80, 90 universities around the world who have signed on with Beyond Benign and what's called the Green Chemistry Commitment, where these leaders in academia of science universities that have come together to try to find ways to change the curriculum, to learn from one another of how to do this. And it's getting bigger and bigger. But these early ones, I am just so proud of the fact that Chulalongkorn University in Thailand is one of the early signers of the Green Chemistry Commitment, and Thailand is on the forefront of this globally, teaching the world that we can have a better future. And so the world needs better, safe technologies consistent with sustainable development goals. Companies want these technologies that are consistent with the UN Sustainable Development Goals. The next generation of students passionately want to make these technologies. Our job is to find a way to get the resources, to get the training together so that the students and us together collectively can make that world that we all dream of having. Thank you so very much for giving me the opportunity to speak with you today. Thank you.
Her Royal Highness Princess Mahachaki Sirinthorn, President of Ram Khamb Heng University, Faculty Deans, Department Heads, distinguished guests, ladies and gentlemen. It is my great honor to be here in this STT Congress. I would like to thank the organizer for the invitation. The topic I would like to share with you today is on the process intensification and multifunctional reactor for supporting Thailand's transformation to bio-circular green economy. In my presentation, I would like to cover three things. The first one is what is process intensification and multifunctional reactor. Secondly, why BCG economy. And the third is the sum of my work in support of the BCG development. This picture should give you a very good overview about what is process intensification. You can see the picture on the left is a petrochemical plant. You can see that this one usually it is big. It requires a lot of resources such as water, energy and others. and it also generates a lot of problems, especially the environmental problems. What we want is to intensify the process to the one on the right. Is it possible to make it happen in just a small size of a container? So this is very important that science, technology, and innovation is very important to make this thing possible. One approach that we can do is to use something we call multifunctional reactor. What is multifunctional reactor? Let's say for a conventional reactor, the main purpose is to convert raw material into our desired product. But somehow in practice, it's not that easy. Not all the molecules go to the product. Sometimes the selectivity, the reaction selectivity is not that high, and also sometimes it is limited by something we call the thermodynamic equilibrium. So for the multifunctional reactor, the way we do is that not only the reaction purpose, we include some other function like the separation function. So with this integration, the performance of the reactor can be much better. A good example is shown in this slide. This is the process for production of methyl acetate. Somehow the production is limited by the equilibrium, and for the product, separation is not that easy. So we got a big trend of the distillation column in order to purify the product. Somehow with the concept of multifunctional reactor, a reactive distillation, which is a unit that incorporates reaction with separation by distillation, can be used for doing this job. Somehow the big process on the left can be replaced by just only one unit operation. So this is a big achievement for this technology. And with this new technology, it can help solving a lot of world problems, such as on the climate change, air pollution, water scarcity, for example. So we come to the second topic, why BCG? I think everyone in Thailand would have heard this term very often, bio, circular, and green economy. Somehow these three concepts need to be considered all together, not separately. But we know that the great challenge for this application of the BCG economy is that it's not that easy. Right now we mainly use the feedstock from fossil base. So it's not that easy that a plant or a company just change directly from the fossil to something like the biomass. It is not that easy. But we know that it is possible if we work together, if we do research, if we can apply this research and align the system to work together, so everyone can do it and make it possible. For our team, it was quite lucky that we got a continuous support from the Thailand Research Fund under the TRF Senior Researcher and TRF Outstanding Researcher grants for 9 years. And this is our team. And after these grants, we were fortunately get another support from NASDA under NASDA Chair Professor Grant. And with this team, we focus on the application of technology platform for selection and development of innovative processes and prototype for sustainable production of biorefinery-based alternative fuels. And this is the picture of our team, as we know that we need to work together with different fields to make it possible. And in this project, let's say we cover about 4 sub-projects on the biodiesel production, biohydrogenated diesel production, hydrogen production, and the last one is basically on the process system engineering to design the new process based on the BCG economy concept. And I will touch just only a few projects to tell you. This is the one on the biodiesel production. Somehow Thailand is doing very well on the biofuel. It is not because we are lucky, but somehow we get a very good foundation initiated by our former king, King Rama IX. he established this kind of project almost 40 years ago, so we get this support. And in the biodiesel production, we know that it is limited by a number of problems. For example, the long reaction time due to the poor mass transfer limitation. So in our research group, we try to develop a number of multifunctional reactors to help improve this biodiesel production. For example, we focus on the ultrasonic flow reactor. We focus on a spinning disk reactor. You can see that with the spinning disk, when we rotate it at different rotational speed, the mixing is getting much better, and it can be applied for the biodiesel production. We also focus on another multifunctional reactor we call rotating tube reactor. And we also propose something we call a hybridized reactive distillation for the feedstock containing high free fatty acid. As we know that the cost for biodiesel production is mainly on the feedstock. If we use something we call something like the waste cooking oil, which is much cheaper, it will be better. So we have to handle the feedstock with high free fatty acid. So the integration of the esterification and trans-esterification in one single unit operation is possible. The other area of our research is on the process system engineering. I will give you some overview. This is some of the project that one of my PhD just graduated. She did the one on the pulp and paper industry. I believe that everyone knows that this pulp and paper industry needs someone to help. As we know that we are facing the digital technology disruption, so the pulp and paper industry needs to survive, and it is possible that we integrate the concept of biorefinery into the pulp and paper industry. And with the integration, it offers a number of benefits, such as it offers the new revenue stream for the company, and also it offers new market for bioproduct and make it more sustainable. The way we study is we just use the computational simulation, and the systematic methodology we use is based on 3 steps. The first one is on the synthesis, design, and innovation. I will briefly just show you that for the synthesis step is mainly to gather all information that what can we produce from the biomass, from the pulp and paper, what is the processing route that can be used in order to produce the bioproduct that we select. And we gather all the information together and put it in something we call the superstructure. And with the superstructure, we can use computational tools in order to optimize to find the best product, to find the best alternative route to produce it. And with this one, when we get the right route, the right product, we can further simulate the process without doing the real one. And by simulation, we can find what is the problem that we should address, we should solve. We call this one the hotspot. For example, if this unit operation requires a lot of energy, we can help solve and design a new process. And this is some of the result that we get it from the pulp and paper industry. And maybe I will finish my presentation by the conclusion that with the process intensification and multifunctional reactor, we can see that it is a good research area that can be good for supporting the development of BCG economy. And this kind of research cannot be done with the support of a number of research grantors, and also by the collaboration with many institutes, universities, and surely not possible by the dedication of our big team, our family. Thank you very much for your attention.
Her Royal Highness Princess Mahachaki Sirinthorn, may it please Your Highness, distinguished guests and ladies and gentlemen. So it's my great privilege that I be here to give a lecture on the topics on the topic that I'm going to speak is on fundamental research in food chemistry to innovation that expand new horizon for Thailand food and feed industry. Actually, my intention to speak on this topic is that I would like to show and demonstrate that how the basic knowledge that we have can be translated to innovation and create the impact for Thai business. My talking point, we have 4 points that I would like to cover. The first one is about the overview of Thai food industry and its current horizon. And the second one is construct a building block from fundamental research to the innovation, just to show how that we can translate those kind of knowledge to innovation. And the third one is that what is the benefit and the impact that we have done. And the last one is the conclusion and the future challenges. For this one, actually just to give you an overview of the Thai food industry, you can see that Thailand ranked number 11, and for the values of about 31 billion US dollar. When we compare with the global export, it's only 1% of those value. And basically, if we look in the detail, we can see that basically Thai export commodity products, so which is low value. So this is what we need to, that's going to be reflect on the challenges that facing food industry right now. So then from this slide, you can see that, so we do have the problem on the productivity. So then we have to increase the productivity. And also we have to increase the process efficiency to reduce the loss and waste. And also we have to do more on research, development and innovation that can leverage the value of the product that we export. And those can do with the product that is the current need of the global consumer trend, that you can see that consumers are more focused on the health, safety, and on the personalized diet and for the need of each of them. And these are the things that when we develop the new product, we have to consider on. From the second part, I would like to demonstrate that how that our fundamental research can be translated into the innovation. Basically, I have been in this area for about 20 years. So I would divide it in 3 phases that you can see that number 1, 2, and 3. For the first one, normally it's going to be like a 7 year each. The first 7 years that I've been in the area, I basically focus on basic research. I working on basically on Thai fermented product. So starting from Nam, and the second one is Tua now, which is fermented soybean in the north. So with my knowledge on food chemistry, I focus mainly on the change in the component of that raw material and see what is the key reaction that important for the sensory property and the quality of those products. By doing that, so I have know the specification of the product that we need, and also that we have learned a lot from the microbe that very important to convert those materials into the fermented product. And we have a set of tools that we can use to monitor the fermentation process and the quality of those products. The phase number 2, the second phase of my life, my work, so I focus on, by using those a strong foundation on that knowledge. So I converted working with the private company, try to solve then challenge myself with the problem that they have, try to improve, increase the product that they produce. From this stage, there are lots of the licensed technology that it can be used and produce the marketable product, such as fish sauce and fermented vegetable with high quality, and also the enzyme that we use in animal feed. And the third one, another 7 years that I think I combine the foundation that I have from the first 2 stages to expand myself to other areas like working on the commodity such as egg, to do like an egg innovation that try to utilize the whole egg and also the byproduct from egg for producing the high value product and functional ingredients. And another one is that related to meat innovation that I mainly working on the quality of meat and the defect that affect on the quality of meat. So that kind of the overview that what I have done for 15 years. 20 years, and also that during the time, so particular on the fermented food, so I'm really enjoy that we could have chance that we can find the novel bacteria with specific activity that we can use for specific reaction that we need to improve in the food. So in this slide, you can see that so far I have found like 9 novel species of bacteria from Thai fermented food product. So to do that, for translation, I think we should have the right tool and the right strategy that to do. In our case, in my case, that I have like starter, which is bacteria. I use cells, enzymes, and other product of the microbial that the cells produce to improve the quality of the product, the value of the product. So this is the pipeline that we normally do with the starter culture or microbe, beneficial microbe. I call RDIMC. Is that research, development, innovation, manufacturing, and commercialization. The success of how to be commercialized is that we have to have the right culture. So screening process is very important. We have to have the robust condition to screen for the one that we need. And also we have to know the whole process, how to use, scale up, and at the end, how to register the product to FDA or the regulatory agency. This the part 3 is about the benefit and impact that we have created from using the cell and enzyme. You can see that actually in the top panels is the one that we already transferred to the company and make the marketable product for like more than 10 years. So the number in the circle is the cumulative impact that make from the technology for like enzyme production, the fermented soybean production by selected bacillus, and the premium fish sauce for export. And the bottom panels is the new product that's still in the commercial pipeline, which is a starter culture and the one-step process for production, the mangosteen cider, and from fruit juice. And the another one is a natural antimicrobial compound from, we call E-lysosome, from the lysosome from hen egg white. So because of the time limit, I will skip the detail on this one, but actually I would like to say that we have to select the right culture. We have to make the process simple that can be do it. And we have to know, in this case, we have the reactor that can be do at 20 to 100 liter. And this technology can be expanded to other food juice. You can see the company that had been involved in the project. So pineapple juice, coconut juice, and or even like a black garlic residues from the process. So another product that we did is we are doing is the natural antimicrobial peptide. So basically we start this one in 2009, but basically I mainly focus on the microbe. But later on, we found that even we discovered the novel antimicrobial peptide with the interesting activity, but it's difficult to utilize in food. So then I moved to change the source to food protein and interested on the AMP that produced from food. So which in this case is a lysosome from hen egg white, that we have the technology that we can enhance the antimicrobial activity of the lysosome and can do the formulation that can diversify the application of this product. This is the pipeline similar to what I mentioned about the starter culture, RDIMC. And currently you can see that we can increase the value of the product, like starting from lysosome, from 3 to 4,000 baht per kilogram to like more than 50,000 baht per kilogram. And this is really nice, actually, technology that we can diversify, as I mentioned. We can combine with the formulation for the new application of this one. In the conclusion, so I think that from those I mentioned, you can see that we can utilize microbe enzymes, create innovation that can improve quality, safety, and the value of the food feed and even the byproduct. And a number of novel microbes with the unique and promising property will be more discovered. To do that, I think for commercialization and food application, we have to concern about safety. And another one is that there's still big room for utilization of microbes and enzymes for food. To do that successfully, very important that we have to have the screening strategy and cost effectively for manufacturing and well-designed thinking, which is very important for the success. And I would like to focus actually to create the great impact, the research and development is very important. We have to have the innovative idea, and we have to know the process, manufacturing, how to manufacturing and how to commercialization by working with the private company. To respond to the SDG, BCG, I think that for BCG food, the government aimed that Thailand should be like hygienic kitchen of the world, so that we have to be prepared that develop that innovation that can create the security, safety, and sustainable food industry. By doing this, I think that it's kind of the formulation. We have to combine what we have, RDIMC with BCG, and SEP is the concept of the sufficiency economy philosophy from the King Rama IX, and with that we can achieve the SDG as we would like to go. And there is the paradigm shift for this one, especially after the COVID-19, is that beyond the competitiveness that we would like to have, we have to expand with the sustainability, security, safety, internal strength, and distributive to the poor and the farmer. At the end, I would like to acknowledge our student funding source and our collaborator in the private sector and the collaborator in Thailand and overseas. Thank you very much for your attention.